topic on forming linear equations, we're going to be looking specifically at using the gradient. So the gradient is basically a measure of how steep a straight line is. So if we look at the diagram on the right hand side, you can see that I've just drawn a basic linear line in black. And what I've done is I've annotated a change in x, which is our horizontal, versus a change in y, which is our vertical. Next to the little light bulb, you can see that I've written our gradient is equal to a change in y divided by a change in x. So if we move back to the diagram on the right hand side, our change in x is denoted by basically a shift from x1 and going all the way to x2. So what has that change been? So how many units has x had to move in order for it to go from 1 to 2? Likewise, if we look at our y value, so we've gone from y1 to y2, and the change in y is looking at, well, what number of units did it have to move from our first point to our second point? So how do we calculate it? So there's 3 different variations of the gradient formula that we can use to calculate it. But before we even go into that, one of the things I need to point out is that when we talk about gradient, remember that it's denoted by the letter m. So if you see m, just think gradient. So the first method we have is m is equal to the rise over run. So our rise is represented by a change in y. So I'll just write rise equals the y, and run is our horizontal, so that's x. So what we're looking at is the change in y divided by the change in x. So then we have our second equation, which we generally use when we have 2 coordinates. And this is where that change in x and change in y come back into play. So the second method is generally used when we have 2 coordinates and no graph, because it's quite hard to visualize the gradient without being able to see it. So no graph. And when I say no graph, no visual. The third method is purely a derivative of, a rearranging of the second method. So all it is the second calculation written in a different form, which is y2 minus y1 equals m times x2 minus x1. To prove that, let's solve for m. So that means I'm going to rearrange this equation and let the entire thing equal m. So in doing that, I'm going to have y2 minus y1 equals m times x2 minus x1, dividing that all by x2 minus x1. That's what I'm going to do to eliminate that, which means if I do it to my right hand side, I must do it to the left. So doing that to the left hand side, I'm left with m is equal to y2 minus y1 all on x2 minus x1. And as you can see, that is equivalent to the second calculation method. Some people find it easy to use option 3. Some might find it easy to use option 2. Just know that you will get the same answer using either or method. So let's look at our cases of the gradient. So we have a positive gradient. So that's the first diagram, which shows a rise over a run. Now our rise, like I said before, is represented by our y-axis. So that's any movement along the y-axis. Our rise, when it's a positive gradient, is positive. And then our run is our horizontal, which is our x-axis. And our run will also be positive. So generally speaking, a positive gradient will be denoted by a line going in the positive direction. Then if we look at option 2, where we have a negative gradient, you can see that I've basically flipped the diagram. So again, our run is still represented by our x-axis, and in this case it can be positive. And then our rise, which is still represented by our y-axis, is this time negative. And that helps us to identify a negative gradient. So again, you can see here that the red line is going down in a negative direction. And again, our rise being negative is denoted by this little arrowhead pointing downwards. We do have two other gradients which I haven't mentioned yet. The first is the zero gradient, so I'll just draw that in purple. It's not a straight line. So this is what we call our zero gradient. And this is represented by an equation y equals a number. And we also have what we call an undefined gradient. And that's represented by, so I'll just write undefined gradient. By an equation that looks like x equals a number. So in this case, it would be a negative number. So drawing the other two equations that we now know, the other two gradients we now know. So we know that this is a positive gradient. Where the formula will be y equals mx plus c. And then our final one will be a negative gradient, which I'll denote by the blue line. And I'll just write that this has a negative gradient. And that will be represented by y equals negative mx plus c. So notice that the difference here is that m is negative m when it's a negative gradient, and when it's a positive gradient, it's just m by itself. So now let's move on to some examples. So in this particular example, we're asked to determine the gradient of the graph. So basically we've got our three options that we can use. Looking at our rise over run method, so by run equals our gradient. So remember, our rise will be the rise between the two values. So I'm just going to annotate the diagram. So our rise is the vertical. So that's a change in our y-axis. So we can see that it's gone from 2 all the way up to 6 when y is 6. So our rise is 4 because it's moved 4 units upward, and our run has gone from when x is 0 to when x is 2. So it has shifted 2 units. So if our rise is 4 units and our run is 2, then our gradient will be 4 divided by 2, so m is equal to 2. Now, the other method we can use is the one that I most commonly use as well, which is the y2 minus y1, all on x2 minus x1. Again, this method does require us to be able to comfortably use our coordinates and calculate the change. So keeping in mind that the order of coordinates is really important, so remember that it's x and y. Make sure that you know which one is going to be your y2 and x2 and which one will be your x1 and y1. So I'm going to say that x1 and y1 will be 0, 2, and I'm going to say x2 and y2 will be presented by 2, 6. So subtracting these substituting these into the equation, I'm going to have 6 minus 2 is equal to 2 minus 0, and m is going to be 4 divided by 2, thus giving me m equals 2. So again, you can see that regardless of the method we've used, m is equal to 2. Now, one of the things I forgot to mention with the first particular equation is we did find that m is equal to 2. Make sure if you are given a graph that you go back and look at the graph. Is it going in a positive direction or is it going in the negative direction? Because sometimes people will find that using the rise over run method, it may be difficult to identify whether or not the gradient is positive or negative. So if you are given a graph, make sure to refer to it. And this is why I particularly lean towards using the second or third equation, purely because if there is a negative gradient involved, then my calculations will definitely show me that. So using the third method just for experience purposes, so we know y2, sorry, it was y2 minus y1 equals m times x2 minus x1. So substituting the values in because I know what they are. So 6 minus 2 equals m times 2 minus 0 will give me 4 equals m times 2. Dividing 2 from both sides, they will cancel out and m will give me 2. So you can see, regardless of the method I use, I will get the same answer each time. So this is a very good checking mechanism as well, if you do have the time to check your answers. But like I said, I tend to lean towards option number 2, and it would be a good one for you to practice because it does involve a lot of your negative numbers, and the little things like that can definitely make or break your answer. So let's move on to another example, and this time we aren't given a graph. All we're told is to find the gradient of the given points where A is equal to 3, 4 and B is equal to, point B, sorry, is equal to 5, 6. So if I do a quick sketch, I'm going to say that 3, 4 is about there and 5, 6 is about here. So having said that, and I'll just quickly label my axes, you can see that the gradient is going in a positive direction, or at least the graph is going in a positive direction. So we should be expecting a positive m value. So our rise, remember our rise is represented by our y-axis, has gone from 3 to 5, which means our rise has risen 2 units. Our run, which is our horizontal, has gone, sorry, I'll take that back. Our rise has gone from 4 units to 6 units. Sorry, so it's gone from 4 to 6, which means it's gone 2 units in the positive direction. And our run, which is our horizontal, has gone from 3 to 5. So again, it's moved 2 units. So substituting these values into rise over run, I get m is equal to 2 on 2, giving me a gradient of 1. Now, let's check that the first method was correct by using the second one. Again, like I said, order is important. So let's say that x1 and y1 is represented by point A, and x2 minus y2 is represented by point B. So substituting these values now into the second equation, we're going to have 6 minus 4 equals to 5 minus 3, and all of that will equal m. Therefore giving me m is equal to 2 on 2, which gives us a gradient of 1. So again, we can see that our calculations are correct for the first and second method. For the purpose of experience, we'll just do the third method as well. So again, using these two assumptions, we're going to have 6 minus 4 in brackets equals m times 5 minus 3. Remember, we're trying to solve for m. So what is m? So 2 equals to m times 2, or 2m. Dividing both sides by 2 will give us m by itself, so m is equal to 1. Again, proving that regardless of the method we choose, we will get the same answer each time. If you are doing a rise over run method, so like the first one, it might not be a bad idea for you to graph a visual just so you know which way the graph is going, whether it's positive or negative. So make sure you are comfortable with identifying where your coordinates lie, where your quadrants are positive and negative as such. So basically, that's it for calculating the gradient. Remembering that the key thing is a gradient does represent a change in y divided by a change in x.